Okay, so the final lesson in Unit 2 is really a cleanup kind of lesson where we just cover a couple of odds and ends topics that we haven't really fully covered yet, and also an important connection that I want to make between the topics that we covered in Unit 2 with the topics that we covered in Unit 1. So the first topic I want to go over in this lesson is how to deal with a solid or a pure liquid in a rice table. You're going to see this quite a bit in the rest of the course, so I want to set it up today in this lesson. So dealing with solids and pure liquids in a rice table. So in this case, we have this reaction with the solid, and it just decomposes in a reversible way to give you ammonia gas and H2S gas, and we have an equilibrium constant for this reversible reaction. So the question is, if a pure sample of the solid is added to a 1 liter flask and allowed to reach equilibrium, what are the equilibrium values of the ammonia concentration and the H2S concentration? So one thing that you can do is, of course, we're going to set up a rice table. Anytime that you're given an equilibrium constant and you're asked something about the equilibrium concentrations, you need to be thinking about setting up a table. So we know that every table has the rows for R, I, C, and E, so we'll get that set up. And each chemical constituent is going to get its own column, so the NH4HS is going to get its own column, and that reacts in a reversible way to form NH3, so that gets a column, and H2S gets a column, so plus. All right, so here's what you do with the solid. Remember, this is a solid, okay? So the way you deal with that really is you just don't do anything with that column. But it is important to, I think that it's important to put in the rice table, and you'll see why in just a second. So once again, we're going to use the same technique that we have with other rice table problems. That's really the unique thing about a rice table with a solid or a pure liquid. You just ignore that column in terms of your calculation. So we are not told about the initial concentrations of ammonia or H2S. So that implies they are 0. Okay, well, once again, if I just do a mental calculation of Q and compare it to the equilibrium constant K, I know that it's going to be, I'm going to use the same expression of the equilibrium constant to calculate a value for Q. And so I take this reaction and I write an expression for the equilibrium constant. And so it's products over reactants. So here's the product ammonia times the product H2S. And remember that the coefficients become exponents. And then, so that's products over reactants, but I leave out solids and pure liquids. So you can either just put a 1 there as a position holder if you want to, or you could just leave that denominator out. And so this is the expression for the equilibrium constant. Okay, just the concentration of NH3 times the concentration of H2S. Well, in this case, each of those is equal to 0. So Q then, which is going to be equal to 0, right? Because 0 times 0, which of course is less than the equilibrium constant K sub C, right? It's a small number, but it's still bigger than 0. And so when that happens, again, remember that means that the reaction goes forward. Okay, the reaction goes in the forward direction, so it's going to shift that way. And if that all seem like just superfluous, that's okay, because if you just figure it out, hey, I start with some of this, I don't have any of my products, so naturally it's going to shift to the right. That's fine. Okay, so here's where I think that just for bookkeeping purposes, it is important to have this column for the solid represented, because if you think about what's going to happen, I'm going to produce a certain amount of ammonia and H2S, so I'm going to have positive values. And I don't know what that amount is going to be, so we'll just call it an unknown X. And if I generate X amount of ammonia, I also generate X amount of H2S, so that's also an X. But you have to kind of account where that came from. Well, it came from the solid ammonium hydrogen sulfide. So we're going to call that a minus X, but I'm going to put it in parentheses because I'm never going to use that in a calculation. Again, it's just for bookkeeping purposes so that I can keep track of where things are coming from and what they're transforming into. All right, so then you just, as every other rice table, you just bring your columns down. And so this becomes an X and this becomes an X. And then if you remember, what I do is I substitute those terms in the E row, substitute the terms in the E row into your expression for the equilibrium constant. So I'm going to substitute that in. So the K sub C is equal to x times x. So that's, of course, x squared, which is equal to 1.8 times 10 to the minus 4. And so then really all you need to do is just solve for x. And then once you get x, you also answer the question, because that's, in this case, x also happens to be the answer to the question. The question asks, what is the equilibrium concentration of ammonia and H2S, which is equal to x? Okay, so now that I've talked through it in a handwritten way, we will erase all that. And we will look at it in PowerPoint. Okay, so we determine the equilibrium constant expression, products over reactants, coefficients become exponents, and I leave out solids and pure liquids. So then I set up my table where every compound involved in the chemical reaction gets a column. My initial concentrations were 0 because nothing was said about the initial concentrations of ammonia or H2S. And so there's the shift because Q is less than K, so it shifts to the right. And so I gain X amount of the ammonia and X amount of the H2S, which means I lose X amount of the solid here. And so you bring your columns down, and then you substitute that into the expression for the equilibrium constant. You solve for X, and so you get a value of X of 1.3 times 10 to the minus 2 molar, and that is going to be the concentration of ammonia and H2S in this flask once it reaches equilibrium. Okay, so now what we're going to do is we're going to use that as a starting point to talk about a situation where the equilibrium is disturbed. And in this case, what we're going to do is we're going to disturb the equilibrium by adding more ammonia into the system. Okay, so if we've got a certain amount of ammonia already in there because it's achieved equilibrium, but then we're going to stress it by adding 0.02 moles of gaseous ammonia into the system. Okay, so once again, I'm just going to set up my table. So my R, I, C, and E, and those will be in my rows. And my columns will be just these compounds. Okay, that gets a column. It reacts in a reversible way to form NH3 and H2S. So each of those gets a column. All right, so I'm going to ignore that column because it's a solid. But now, instead of zeros right here, we know from the previous problem that it was 1.3 times 10 to the minus 2. So that, if you don't mind, we're just going to express that as a not in scientific notation. It's just a normal decimal, okay? So this is my starting point. I'm at equilibrium at these concentrations. But then I come along and I add some more ammonia. So I disturb the equilibrium by adding 0.02 moles of ammonia. Okay, you see what I did there? So that not only the initial amount from the equilibrium that was established, but now I come along and I stress the system by adding 0.02 moles of ammonia. Okay, so then it becomes a situation of, well, if I think about the Le Chatelier's principle, if I stress this side, then it's going to shift in that direction to relieve the stress. So again, if you think about my 2-tank example, if I pour some water in the right hand tank, then water is going to flow through that connecting pipe to the left to relieve that stress on the system. So I'm actually going to lose X amount of the ammonia. Okay, and if I do that, then I also have to lose some of the X amount of the H2S, because to get rid of this, it has to react with this. So if this is negative, then this has to be negative by the same amount. Okay, so it's going to shift in that direction. And so some of these two gases will become a solid. Okay, so that becomes a plus X. Okay, but again, that's not going to become involved in my calculations just for bookkeeping purposes. That if I lose some of these two guys, they become this solid, and so I want to account for that. Okay, so then once again, I just bring my columns down. So 0.013 plus 0.02 is 0.033 minus X, and this is 0.013 minus X. And so just like before, I can just substitute that into my expression for the equilibrium constant. So that becomes 0.033 minus X, and that becomes 0.013 minus X. And all of that equals 1.8 times 10 to the minus 4. And so again, we're just going to solve for X. Okay, but once we solve for X, that doesn't fully answer the question. We are asked what are the new concentrations of NH3 and H2S. So you solve for X, and then you're going to use X in a calculation indicated here. You're going to subtract it from 0.033. You're going to subtract it from 0.013. Okay, so let me erase all that. I'll show it to you in PowerPoint. Okay, so again, our expression is the concentration, the expression for the equilibrium constant is the concentration of ammonia times the concentration of H2S. You set up your rice table, but this time you don't start with zeros, you start with the equilibrium concentrations that we calculated in the previous slide. And then I account for the stress of the addition of the 0.02 moles of gaseous ammonia. That's what this term right here is for. Okay, and so since we stressed the right side, it's going to shift to the left. So I'm going to have a negative change in the ammonia and in the H2S, and it's going to shift to the left. So I gain X amount of this solid. And so like before, you just add your columns down, and that's what these terms represent. Then you just substitute them into the expression for the equilibrium constant, as is shown right here. So you can collect your terms and, and you solve for X. In this case, you don't even really have to plug it into your calculator in the number solve function because it doesn't really involve higher order values of X. But when you do that, you get a value of 6.3 times 10 to the minus 3 for X. And then you subtract that from 0.033 to get the concentration of ammonia, final. And you subtract it from 0.013 to get the concentration of H2S, final. Okay? All right, so that is the example that I wanted to show you about how to deal with a solid or a pure liquid when you're doing a rice table problem. Okay, so the next thing that I want to cover in this lesson is linking together some important topics from Unit 1 to what we have learned in Unit 2. And now that we know about reversible reactions and how they, sort of play out, we can look at special situations in kinetics, reaction rates and reaction mechanisms and things like that, rate laws that involve reversible reactions. We didn't look at that when we learned all of the things in Unit 1. Well, but nonetheless, it happens, it's out there. So we want to go back and revisit that and talk about how it's affected, how all those topics are affected when you have a reversible reaction in the mix. Okay, but first of all, we're just going to do a review of the main thing regarding this this topic that we learned from lesson 1. So one important thing that we learned, if you remember, is that when you have a multi-step reaction, so if you can break an overall reaction down into individual steps, elementary steps, that you base the rate law on the slow step. So for example, if I have this overall reaction where A plus 2B forms this product, we're just going to call D. And remember that, I wrote it down here so that you can see it's the sum of the two individual steps. But this overall reaction breaks down into step 1 and step 2. Okay, in step 1, A reacts with B, okay, to form this intermediate C. And in step 2, that intermediate C reacts with another molecule of B to form product D. And it turns out that step 1 in this example is the slow step. And so as we said above, that the rate law then is going to be based on that slow step. Okay, so remember that when you do that, all right, so you would just say, all right, well, the rate, if you know the step-by-step mechanism, you can just say that the rate is equal to some rate constant times the concentration of each reactant raised to the power of its balancing coefficient. So, those are both 1 in this case. So this would be the rate law, not only for the slow step, okay, but also for the overall reaction. The rate of this doesn't even matter because the overall reaction is going to be determined by the rate law of the slow step. Okay, remember we called it the rate determining step. Okay. All right, so the rate law would just be the rate equals the rate constant times concentration of A times concentration of B. All right, well, all that was just review. So now what we want to do is we want to look at how it changes in some situations when you have a reversible reaction for a step. Okay, so in this case, let's say that step 1, A plus B in a reversible way, okay, gives you C, and that's the fast step. But now the intermediate C reacts with another molecule of B to give you product D, and that's the slow step. Okay, and so once again, if you just add the reactions together, you get the same overall reaction, but in this special case, one of the steps is reversible. Okay, so once again, we can write the rate law based on the slow step. Okay, the rate is equal to the rate constant times the concentration of C. Okay, remember, you just take the concentration of each reactant times concentration of B. Okay, raised to the power of their stoichiometric coefficients, so 1 and 1. But here's a problem, because C is an intermediate. Okay, so I will never really observe C. If you're trying to control this, if you're trying to monitor the progress of this reaction, you won't be able to really do that because C is an intermediate. And so if the rate is based on an intermediate, then you would never even know it, because you can't control the concentration of C. You can't like double the concentration of C and see how it affects the rate, right? Or you won't even be able to observe it because it's produced in an early step and then consumed in a later step. It's an intermediate. So that's a real problem. So how do we deal with that? Okay, let's talk about it. All right, so again, the rate law would be based on the slow step. Rate equals the rate constant times concentration of C times concentration of B. But C is an intermediate, and therefore it cannot be controlled. So there's no way to confirm this mechanism. But there's a solution that we'll talk about now. Okay, so the solution is that we're just going to express that concentration of C in terms of the concentrations of A and B. How? By rearranging the equilibrium constant expression that we can get from step 1. All right, so let me go back to my pen here. So if I were to write, this is a reversible reaction, okay, so it can establish an equilibrium, and its equilibrium constant expression would be the concentration of the product over the concentration of each reactant. Okay, right? Products over reactants, coefficients become exponents. And so we're going to assume that these are all, solutions, right? Not or gases, not solids or pure liquids, right? So what I can do now is I can just rearrange this, and I can say, all right, well, the concentration of C then is going to be equal to the KEQ times the concentration of A times the concentration of B. See what I did there? I just multiplied both sides by the, oops, forgive me. I multiplied both sides by the concentration of A and the concentration of B. Okay, so now that cancels. Okay, and I multiply this side times concentration of A times concentration of B. Okay, so this gets multiplied by that. You see, so you just use algebra to isolate that. And so now you're just going to substitute this into the rate law. So we're going to substitute that in right there. Okay, and so when you do that, you get something that looks like this. The rate would be equal to the rate constant times the equilibrium constant times the concentration of A, okay, times the concentration of B times the concentration of B again, okay, because this is the part that I substituted in. Okay, so we're going to do two things. First of all, we're going to combine these two and just make it a concentration of B squared. But the other thing we're going to do is we're going to smash those two constants together, and we're going to call that a K prime, right? Because it's just one constant times another constant is still just a constant. So we're just going to represent the fact that it's a different constant by just putting that apostrophe on it. It's called K prime if you want. So this would be the rate law of this overall reaction based on the concentrations of our initial reactants. And we use the expression for the KEQ to get there, because once again, I cannot base a rate law on the concentration of an intermediate, because I can't control it, I'll never observe it. And so we have to get the rate law in terms of the concentrations of reactants that I can actually observe and control. And that would be, in this case, A and B. Okay, so now we'll look at it in PowerPoint. Oops, nope. Okay, so the expression for KEQ would just be the concentration of C over concentration A times concentration B. So I rearrange that, and you get concentration of C equals the equilibrium constant times concentration A times concentration of B. Okay, so now we're just going to substitute that into the rate law. Okay, and so I substituted it in right here. So concentration of C equals this. So I substitute that in right there. And as I said, I smashed together the two constants, and there was a concentration of B in there, so that's why I made that a concentration of B squared. Okay. All right, so here's just another example. So in this case, we have the decomposition of ozone. So ozone is this molecule that's in the upper atmosphere that shields the Earth from a lot of harmful UV radiation. And so it can decompose into oxygen according to this reaction. But it happens in two steps, and one of those steps is an equilibrium fast step, you see. So first of all, what happens is the O3 reacts in a reversible way to form an O2 and oxygen atom. All right, but then another ozone, okay, so this would be a second ozone, right? Two O3s, so this is the second ozone, finds that intermediate, that oxygen atom, and what it does is it reacts in a one directional way to give us two oxygen molecules, and that's the slow step. So once again, if we wanted to write the rate law, it would be based on the slow step, okay? If you're gonna write the rate law, it's gonna be the rate constant times the concentration of each reactant. So it's O3 times concentration of O, all right? But the problem is this also is an intermediate, and I can't have a rate law with an intermediate in it because I can't control this, I can't observe this. So I need to find some way to get rid of this oxygen atom term. But the nice thing is it shows up here in this reaction, and I can use the equilibrium constant expression for this reaction and rearrange it to express it based on that concentration of oxygen atoms. So for step one, the equilibrium constant expression is the concentration of O2 times the concentration of O products over reactants, so over the concentration of O3, okay? And so just rearrange this to isolate that term right there. Okay, so we're going to multiply both sides by the concentration of O3 times concentration of O3. And so that cancels on that side. And so now I'm just going to divide both sides by the concentration of O2. Concentration of O2, so that cancels. And so I can say that the concentration of oxygen is equal to the concentration of O3 times the KEQ divided by the concentration of O2. All right, so now I can substitute that in right there. Okay, pardon my penmanship. And so if you do that, you get the rate is equal to the rate constant times the concentration of O3 times this, times the concentration of O3 times the KEQ divided by the concentration of O2. Okay, so the two things that we're going to do is we're going to smash together both of these equilibrium constants. We're just going to call that, K prime. And then once again, I'm just going to, put these two terms together, and that would look like this: concentration of O3 squared over the concentration of O2. Okay, so I'll let PowerPoint make that look nice and pretty, but that's how you could express the rate law in terms of things that you can measure. In this case, we have to also express it in terms of a product, a final product, but I can still measure that. The whatever instrument I'm using to detect O3, I could probably have it also detect O2, or you can use some method at least to detect the presence of O2 and the concentration of O2. But the problem with the oxygen atom is there's no way to do that because it's an intermediate. It's produced and then consumed. I can't control it and I can't observe it. I can't observe the amount of O3 and the amount of O2. So I can write the rate law based on those components of this chemical reaction. Okay. So this would be the rate law based on the slow step, but the oxygen atom is an intermediate, so I need to get rid of it. And the way I'm going to do that is I'm going to express that concentration of oxygen atom in terms of the other things that are involved in the reaction. And I do that with the equilibrium constant expression from step one because it is a reversible reaction. Okay, so this is the expression for the equilibrium constant of step one. And then I just rearrange and I isolate the concentration of oxygen atom, and it looks like that. And so then I just substitute it in, and as you can see, you get the same answer that I wrote originally. Okay, so what I'm going to do is I think that this is going to be a good one for you guys to try on your own. If you want, just pause the video and do some work on scratch paper, and I'll show you the solution in just a second. Okay, so once again, in this problem, the key here is to recognize that your slow step is right here. So that's what your rate law would be based on. Okay, but it's got an intermediate in there because N2O2 is produced in step 1, but then consumed in step 2. So that's going to be an issue. Okay, so if I were to write the rate law, it would be the rate constant times the concentration of H2 times the concentration of N2O2. But N2O2 is an intermediate. So we're going to use step 1 and the equilibrium constant from step 1 to rearrange and express it in terms of the concentration of N2O2 so that I can substitute it in for this term right here. Okay, so from step 1, the equilibrium constant would be the concentration of N2O2 over the concentration of NO squared. All right, so rearranging that, solving for the concentration of N2O2, you get that the concentration of N2O2 is equal to the KEQ times concentration of NO quantity squared. Really, we just multiply both sides by concentration of NO quantity squared. So now you just substitute that into the rate law. So that part right there, you just substitute in right there. Okay, and then you combine the constants. So you smash together that K and that K, and then you end up with the K prime times concentration of H2 times the concentration of NO quantity squared. Okay, so we'll stop there, and based on what we learned in this lesson, you should be able to finish up the homework assignment in Chem 101, and also that's all that you need to know to do the other extra practice problems as well.